We're going to introduce Mike Keith in a minute, but just to start, this is the agenda that Mike promised to talk about. He's going to show some extremely short programs that compute approximations of pi and do pretty well. He's going to talk about some elegant approximations of pi, fractions and other formulas that contain few digits but give you lots of digits of pi. He's going to explain some more examples of Pilish, that's constrained prose, where the number of digits in each word is the next digit of pi. Accidental Pilish is examples of people who wrote little fragments of sentences that were in Pilish, but they didn't know that they were doing it. Finally, the last topic Mike's going to talk about is memorization, because if you want to memorize and be in contest with lots of digits of pi, there's some memory tricks that Mike can tell us about. Before getting into the main agenda, Mike suggested this little puzzle. He was typing away on an online calculator, and he got an interesting result from this strange division, right? 1 divided by a whole bunch of 5s, right? And then press the sine button to take the sine of that angle. Why do you get all of these digits of pi? Oh. So, everybody kind of scratched their head about that for a minute. There is a reason, and Mike goes on to explain this a little bit more in a minute. But the mathematical answer has to do with the fact that 1 divided by a whole string of 5s is a number that's very small. Sine of a very small number is basically the same number, except it's got to be in radians. If you're talking about degrees, then you have to multiply that number by pi over 180. And sure enough, all of these 5s give you a number that's like 180. It's smaller. It's like 180 times 10 to the minus 11th or whatever. And that's where, when it converts that into radians, and then does the sine operation on it, that's why you get all of the digits of pi out. So here's Mike to explain this exercise and also give us a little bit more information about the rest of the agenda.
Let me just make a little expand on that a little. As you said, powers of 10 don't matter because we're just, see, there's a 1e minus 17 there that we're ignoring. It's just why are the digits of pi there? It's the question we're asking. And one way to look at the 555 part is what fraction is 0.5555? Well, that's 5 over 9. And we're taking the reciprocal, which is 9 over 5, which is 1.8 times 100 is 180. Now you can continue. Or maybe we're sort of done.
Yeah.
Okay, but let me that was all very good. Let me just add one more thing in, because I see a few quizzical looks still. So after we got to the 180, the other key point you have to ask is when you do a sine of something, did you have it in degree mode or radian mode? And it's ambiguous from the slide, but because this button could either mean go into degree mode, which means I'm in radian mode now, or it could mean you're in degrees mode now. But that's what it actually means. It was in degrees mode. So we're and then the third tidbit you have to realize is when you have a calculator and you do a sine in degree mode, the sine is only defined in radians, so it has to convert from degrees to radians, which is multiply by pi over 180. But we've got 180, and we multiply it by pi 1 over 180, so you get pi.
We need to.
So that was that. Thank you for your help with that. I'm not going to bother telling you what I'm going to say. I'm just going to say it. So I'll skip that stuff. This year I wanted to do something a little more interactive and a little more um, related to algorithms. Last time I talked a lot about the digits of pi themselves as an object of affection. And that thread is still going to be here this time, but have some more concrete things to show you. But everyone who learns about pi, the first thing is to be interested in, what comes after the 314 or the 314159 that I already know. And of course, there's an infinite number of digits, and they're all mysterious because they behave exactly like uniform, independent random numbers. That is an empirical observation at this point in mathematics, because it has never been proved in the sense of a mathematical proof that that pi's digits behave like independent uniform random numbers. They do empirically. Like I said, you can take the 31 trillion that have been computed, and indeed they don't, the statistics of those digits don't contradict the assumption that pi is random. If you look up and read more about it, the term that's actually used is normal. And normal is even stronger than independent uniform random numbers. But anyway, so I said I was going to get into some real stuff this time. Here's the first one. What does this program do you think? And I'll start with a much easier one. What language is it in? Which is obfuscated a little bit by wrapping it into a rectangle, but it should be pretty easy. The answer has already been given by Dennis.
Yeah.
It is, of course, Python.
It's in Python, yes. Because you can have several expressions with commas in between them.
Yes, yeah. The tricky one's the second line here. I am not at all fluent in Python, but so I learned for the first time that you can put a while on one line, and you can put the I minus equals 1 on the same line too. Yeah. But there's no indentation, no wasted space characters. In the 56 characters, the 2 pink blocks, you can think of those as the new lines, so those are even included. So, of course, I tried to make this as small as possible, and 56 was as low as I could get. But not being a Python expert, there might be 1 or 2 more characters that could be shaved off. But now the question is, now that we unwrap it like it shows on the bottom here, can you see my arrow? Yes, you can. Now that we unwrap it into normal code, you can't run it like it is either. It won't compile, broken up into lines this way. But if I can navigate this weirdness I've got here now, I want to get down here and hit this button. This is a wonderful resource. I don't know if everyone knows about it. It's called TIO, stands for Try It Online. You can run code in any one of 500 languages. Here, I'll hit the button. Here's the list of languages, including all the big ones and then really obscure stuff as well. Now, what I don't know is how to get back, because I've never hit that button. That do it? There we go. So I'm just going to hit the run button, and we'll get the answer to what does this program do. That's all 768, as I just showed you in that circular diagram. So I think objectively, this program is very, very cool. And so let me show you a little more about it. First of all, how in the world does this work? Why does it work? And the answer is not very complicated. It goes back to a formula from Euler way back in 1748. The second line here, we've simplified the summation. By we, I don't mean me. Somebody figured out how to simplify it. It's not a very complicated thing. You get rid of the square on the n factorial on the top. You get rid of the powers of 2 in the numerator. You change the factorial into a double factorial. And you change the pi into pi over 2. And then the real nice step is you just write that out explicitly instead of as a summation. And you see it's got a nice, fairly simple form. And then I think it wasn't until a paper called The Spigot Algorithm for Pi by Stan Wagon in like the 1980s or somewhere around there. He said, you can take this and express it even more simply like this. We've got a lot of nested parentheses now, which looks a little confusing, but it's even more simpler. We've just taken the 1/3 and factored it out and put it here because it appears in every term and so on. And then I've taken the 2 and multiplied it through here. So it's now pi equals something instead of pi over 2 equals something. And this is very simple now. It kind of looks a little bit like the first infinite series ever constructed for pi by Leibniz back in also the 1700s or 1800s at least. And that's this thing here. But the difference is the Leibniz series is like truly the worst converging series ever. Not literally true, but it's really bad. You don't want to know how many terms you have to use to get like 8 digits of pi. But this series is actually quite good. It's not as good as the ones that are used to calculate 31 trillion. Those converge even faster than this one, and quite a lot faster. But this is not bad at all. You just saw us run that, and it took like a 50th of a second, including the fact that we had to transmit the program to this thing's server, and it ran it on that server and sent us the result back. So this is a really great formula, and for this fun problem that I'm describing to you as a fun problem just in itself of trying to calculate the digits of pi with the smallest code you possibly can. It's also really great for that. So the trick, as I say at the bottom here, is you just multiply both sides by a large power of 10. And now all you need is arbitrarily long precision integer arithmetic, which is built into Python, which is why I used Python and not C or something else, or Java, because those don't have arbitrarily long integers built in. They have libraries for it, but not the real thing. So you just run this in Python and it works. You multiply both sides by a big power of 10, so the left side just becomes, let's say 1,000, 10 to the 1,000 times pi. So if you calculate that as an integer, you get the first 1,000 digits. Do I want to switch to that next? Yes. So this is really cool and really great. Next step you can say, what's the shortest program I can write for calculating pi? And I'm going to use the same method because it seems to be the best method there is, using any one of those 500 languages. Now I've got another huge degree of freedom to play with. Did I have time to learn all 500 languages? No. I did some study for a day or two, and I said, this looks like the most possibly best candidate out of those 500. And I'm not an expert on that language because I thought of this just for this talk, and I just did this 10 days ago. So I didn't even have time to learn this one language fully, but I think I did a pretty decent job. Here's 16. This is a language whose name is a hexadecimal number. And the language was like many of the more obscure languages on that list of 500, not many, a few languages on that list of 500 were invented specifically for a game in programming that's called code golfing. Code golfing just means you take some algorithm that you can write down in pseudocode and try to do it in as few characters as possible. Your score is the number of characters. That's why it's like golf. So there are languages classified as code golfing languages made specifically for that purpose. And one of the common features is they're stack-based. That gets rid of all parentheses that you might have to use, which is great. And it allows you to do little tricks like the bottom line here of my comments. This is my commented version of this code, which we're not going to go over, but the last line points out that yet another trick a code golfing language will use is when you get to the end, it prints whatever's on top of the stack. That saves you the characters it takes to print something. Even more clever, if you have a loop, a while or a for loop going, it terminates that without having to put an end or a curly bracket. So this one is so cool that I thought we needed to run that also. So I think I've got the right one. Switch over to here. I've already pasted it in. And now this one we can use in the 4x4 grid because these code golfing languages usually care nothing about white space. You can have white space and have new lines, or you can not have it, whatever. It still works. And just to make it even more cool, I said, well, now I've got it down to 16. What's the most number of digits of pi I can do and still stay within the 16? I was able to get it up to 1,000, which is not a huge increase, but we're going to run it. And this is going to take 2 seconds or 1 second or 2 seconds because it's running this language as an interpreter instead of compiling it. I don't even know if a compiler even exists for this language. There's a bunch of interpreters for it. But there it is. That's surely, like me, you know that this is correct because it ends with 0198, right? No, you don't? Oh, well. I do. Okay, so, whoops. So that's pretty cool.
It's pretty cool.
I went up to 1,000. Now there's the next one. You can say, how much could I reduce it? Not down to something trivial like 10 digits of pi, but how much can I reduce it so it's still a significant number of digits and get it down to even less than 16? Because there's two numbers in here, this 4096 and this 999, that in this great code golfing language doesn't take 4 digits, 4 bytes and 3 bytes. It takes 2 bytes and 2 bytes, actually. But if I reduce those numbers, I should be able to eventually get to a point where it'll be 1 byte and 1 byte, so now I've saved 2 more. And the answer for that is around 256. So I did one for 256 digits, which I won't run for you, but I'll show you the result. And of course, when we got it down to 14, we can say, there might be something more interesting than a 4x4 square we could do with 14 things. And indeed there is. So there's the 14 character version. I believe you are seeing a new world record for the shortest program to calculate the digits of pi. I don't know that for sure, but I did enough searches on code golfing forums and stuff, and I definitely did not see a 14 anywhere. Okay, totally different topic now. Not totally different, slightly different. When we're looking at, sort of economy and doing things with small numbers of letters or small numbers of bytes or small numbers of digits. An interesting question is, how well can you approximate pi using a small amount of material? In this case, the material are going to be numbers themselves. So this is a famous one. I have no idea who invented it, but like almost everything interesting in math, it was communicated to the world by Martin Gardner. So the trick here is, you know your odd numbers. You know the first three odd numbers. That's all you have to remember. Just have to remember 1, 3, and 5. And then you replicate each one. So you get 1, 1, 3, 3, 5, 5. And you put the old-fashioned, and yes, a lot of us are old enough to remember the divide into symbol as opposed to the divide symbol. You put the divide into symbol in there, and then you do it, and you get 7 digits of pi. And there's some semi-deep math that explains why this particular fraction works. There's a thing called continued fraction, which is this thing on the right. It's kind of like that other formula where you have a nested thing going on. But every real number has a unique continued fraction. And the numerators are all 1. And then whatever these numbers are down the diagonal are just whatever they need to be to make the real number that you want. So every number has a unique representation as a continued fraction. And that representation is these numbers on the diagonal, which you can just write linearly this way. And there's a, like I say, fairly deep theorem in mathematics that as you go along and you get to a term that's relatively large, like this 292, if you throw away that large term and all the ones after it and just calculate this fraction with the 3, 7, 15, and 1, you will get a surprisingly good approximation for, for the real number that you want from a small number of digits. So that's the reason why this cool thing on the left-hand side exists, is because of this 292 right here. And importantly, again, we're trying to be really efficient and cool about things. Importantly, we got, even if you count, I said all you have to do is remember this, but you could say, well, what you really are remembering is this. But we've gotten 7 digits out of putting in 6 digits. So that's a cool thing. Can I find some collections of numbers that I can do a calculation on of digits and get some number of digits, correct digits of pi, and get more correct digits than what I started with? So that's the next fun recreation. And here's the next few steps in that progression. We just define the efficiency as the number of output digits over the number of input. And you'd like that to be more than 1, which it is for 355 over 113. It's 7 over 6, so that's more than 1. This next one is probably the coolest pi approximation in the world, at least in my opinion. It's 5 digits going in and 9 digits, correct digits coming out. But actually, there's 11 correct digits coming out. Bizarrely, and just by luck, this 5/8 is also correct, and the 2 is only off by 1. Now, we're computer scientists, right? Do we like off by 1 errors or not? Yes, we do when they do something cool like this. This 2 is supposed to be a 3, but hey, it's close. So you've sort of got 5 digits coming in and 11 digits coming out, or 12 if you say, well, I'll just error correct the 2 to a 3 in my head. So that's really cool. And we can go back and connect this to the one I just showed you, because the whole reason this one exists is that pi to the 4th has a ridiculously, incredibly large number in the continued fraction. early on. And that's why this works. And this, of course, the 16539 was discovered by Ramanujan, because that's the kind of thing that's the kind of thing he was all about. And then you take that fact and just you just invert the thing. So instead of pi to the fourth, we have the fourth root here. But that's where this great approximation comes from. And so both this one and this one are based on the continued fraction thing. Can you do even better than that, 1.8? You certainly can. Here's 12 digits going in and 31 coming out. And this one is, if this continued fraction business is deep mathematics, the square root of 163 is really, really seriously deep mathematics. Do look it up for yourself with the word Heegener, H-E-E-G-N-E-R. There's only 9 Heegener numbers, integers, period. And that itself is a very deep theorem that was proved. There's only 9 of them, and 163 is the largest one. And the larger the Heegener number that you use, the better approximation you get. And it has to do with imaginary quadratic fields of the square root of q. It's very deep stuff that I don't pretend to understand even. But that's what makes this one work. So it's really cool that these exist, not just that they exist, but it's well understood as to why they give you such a great approximation for pi. Dennis, can you kind of be my time person? I was going to have a clock here, but I forgot to do that.
I'll give you a 10-minute.
Great. Okay, two main topics left, I think. One is this thing called Pilish. The first person to ever think of writing a sentence like this, we don't know who it was, but it was someone about 100 years ago, 1930s or so. And this was the sentence he wrote, except you might imagine I changed the last word to update it by 100 years. Trivia question, what did it used to say? Exactly. All right, quantum mechanics. Because that was a big thing in the 1930s. So you see, since I've annotated it here, what's cool about it? The number of letters in the words are 314159. And the first time you see that, you say, of course, that's cool. Let's keep going, right? How just like how many digits of pi can you compute? How much of this thing can you write? And that's the thing that this group Oulipo has been all about since the 1950s. Almost all French writers. Georges Perec is one of the most famous, but there are many others. So this becomes that kind of, once you learn about Oulipo, then that helps you get your head around this concept of what are different interesting ways to make potentially long texts that follow the digits of pi. There's 2 little problems you have to overcome first, though. What you discover immediately when you get to digit 32 or 33, you discover the first one anyway. And those 2 problems are, whoops. Okay, before I talk about the 2 problems, I'll show you a couple other nice little texts before we get into the really long stuff. The very first thing a person that's into this Oulipo kind of stuff thinks is, you've given me one constraint. I have to write the text so it's 314159. Okay, fine, I understand that. Okay, now I can do that. Let's add another constraint on top of that. And that could be anything. But a simple one is poetry. Poetry itself is a constraint. The language you use, the cadences and so on, but especially the rhymes. That's what everybody thinks of a poem as, something that rhymes. So these next two slides are two really excellent poems that are also Pilish. And a poem that is Pilish, you might want to call that a poem. Both of these poems I'm going to show you were written 30 to 50 years ago, and I couldn't help it but to try to polish them a little bit and make them better. I won't go into, telling you all the words that I changed and things that I added. This one I didn't change too much. I changed the last two lines quite a bit. The second line, which is especially lovely, I think, is entirely Joseph Shipley's. But it paints this really nice picture. The end rhymes are A, B, A, B. So it's night and right and opportune and plenilune. Plenilune is an obscure word for the full moon. So it's, people wandering around at night, the church bell goes off, and this other stuff happens. So that one is really nice, I think. And this one came a little bit later, right around the same time. And oddly enough, these two that I think are some of the best ever written both have to do with astronomy. But that's just accidental. This one includes the word pi, which is also cool. Okay, now let's go back to those two problems I said. These two poems, these two writings didn't have a problem, didn't encounter either of these problems. But just a couple of words later, you encounter the first one, and then eventually you encounter the second problem. First problem is, what happens when the digit of pi is 0? You have to do something to represent that, but I didn't say what that is. And what I think is a pretty obvious choice is what's become the common convention, is what's used now, which is a 10-letter word. You take it mod 10 and you get a 0, so it represents the digit 0. The next interesting one is, and that all the 10-letter words here are in red to show you how many of them there are. And this is a whole topic that I wish I had time to talk about. But at a higher level, what this does to your process of thinking as you're writing Pilish is very important. You have to use a lot more long words than you would in normal English, because 1 out of every 10 words is going to be a 10-letter word on average, and that's a lot. And that's why there's so many red words on this page. But the second problem that we can overcome is at the very, very, very end here, the very last word. Don't look at the word yet, look at the digits of pi. It's a 1 followed by a 1. If we didn't add the rule that I'm about to tell you about, every time you got to a 1 followed by a 1, there's only 2 words in English that are 1-letter words, A and I. And don't come to me talking about the archaic O without the H, because that's not very nice. So you've got I and A, and you can't even put I and A next to each other in a sentence very nicely. So it's just a real pain. So the one more handy rule, as I say here in the title, is that a 1-1 can be an 11-letter word. Makes total sense. You can translate from words to numbers, to digits unambiguously. It's not a problem, works great. Sometimes we use it for 12 and 13, for 1, 2, and 1, 3 as a 12 or 13-letter word, and that works great. So with that, now, the sky's the limit. You really can write forever in Pilish traipsing through the digits. There's no problems whatsoever. It's just up to the amount of sweat that you want to pour into working through this constraint. And as an example of that, there is a book you can find on Amazon. You might recognize the author's name. That goes to 10,000 digits. And this thing here is the very first words of that book. It's poetry, prose, a whole combination of a lot of things. I deliberately change genre every 1,000 digits to make it more interesting. So, okay, another kind of related, very related, but slightly different topic. Okay, now we've got to the point we can write anything we want in Pilish. We can ask, have there been people who wrote Pilish by accident? And the answer is yes. One of the nicer ones I didn't put here is from H.G. Wells. I think it's The War of the Worlds. Maybe it's a different one. But that wasn't long enough here. I wanted to show you the very cream of the crop. So this one is, I think, kind of the second biggest world record. It's easy to find accidental Pilish right in the middle of a sentence, but it's much nicer if it starts right at the beginning of a sentence, as it does here. And this was way back in 1769. He had no idea what he was doing, but there it is. And here's the two current world records. They're tied because they're both 10. And these are very modern. One was written in 2009 by someone who had no idea what he was doing on an online model railroading forum. And the bottom was written by somebody who didn't realize what they were doing on a diabetes forum. And there they are. That's the current world record. You'll notice that the top one uses the trick of 1, 1, and 1, 1 and 2. It actually has a 15-letter word in it. These are all unintentional. But there they are. They're still perfect Pilish. Very good question. The first one, since I found, I can answer. I'm not sure about the other one. It's not going to be the answer you expect, I don't think. A very manual process where I tried to think of what might be a good start to the sequence of Pilish starting with the 314. And in this case, in this particular case, I think I based a lot of it on the 15. I said, what's the most common 15-letter word, period, that I'm likely to find on the internet? And straightforward seemed to be a good one. And I think I didn't use the U. I probably just did a plain old Google search for a very straightforward. And maybe I figured out the procedure too. And that was it. I just scanned through the search results. Yep. No fancy scripts or anything. And like I said, the bottom one I'm not sure about, but possibly similar. So now another little weird thing you can think of. This is again just a slight alteration on this little challenge, which is, but it's similar, because if somebody's going to write it accidentally, it has to be kind of natural English. But this is a slightly different challenge. What's the most perfect Pilish, meaning, and perfect Pilish is when it's indistinguishable. You can't tell that there's any constraint. It sounds 100,000% normal English. What's the most perfect Pilish you can think of? We want it to be fairly long, but we know it's not going to be huge. that is not only accidental like this one, but you could very easily, very easily encounter this accidentally, like in real life. So this is just my offering as an answer to that. I think it's I think it's quite good, but I'm absolutely sure there's better ones. But this is my current favorite. Somebody could say that you would not notice anything, but it's there, it's Pilish.
Chat, they're saying, now I want a snack.
Time for pie. Okay, so now you know my level of obsession, right? So now I'm watching TV with Barbara, my partner, and we really like foreign stuff, um, shows or films. So they always have subtitles. Because don't make me go there about watching foreign stuff dubbed. Don't make me do that. So um, I, of course, can really spot these now when they pop up in the subtitles. And this is just 4 examples of many I've got. Probably my 4 favorite ones. Every one of these starts at the beginning of a sentence, which is super important. And the one on the upper right, except for the fact that it doesn't have a verb, both starts and ends with punctuation. The person wearing pink has just asked that other guy, I know you're really big into rugby. Can you tell me what really, what really inspired you to be a fan of rugby? And that's the first words of his answer. So that's that. Besides TV shows and stuff, here's an accidental Pilish book title and an accidental Pilish movie title that both actually exist. And taking a tiny little jog over here to something slightly different, we've got accidental occurrences of the digits themselves. I don't know why. I can't believe that everyone making all of these occurrences of pi did it as a pi Easter egg, but maybe they did. Who knows?
314 sounds kind of random,
It does.
but it's been impressed on us from when we were that high, right?
Right, right. It's a whole interesting question as to why it's so prevalent. Who knows what the bottom right one is? That's my all-time favorite. You see the 314, of course. Also the 315, because that's the way hotel rooms are numbered. That's the one across the hall. Twin Peaks, you got it. Dale Cooper stayed in room 315. This is episode 1 of the 2nd season when he's laying on the ground after being shot. And this old guy, spends like 7 minutes while he's laying there dying, trying to help him or failing to help him. But there's the 314 across the hall. It will not surprise you at this point that I have this dollar bill in my possession. I found it by looking at them every day for years. Yes, way. And it's got exactly the ones that most people know, the 314159. The next one is wrong, and the 0 at the beginning is cheating. But still, I'll take it. I don't know offhand. It's pretty low that somebody would find this. It's not very low that it exists. They just meant them, and you've got all of this so many, and of course one of them is going to be that. But the chances of finding it is pretty small. Okay, last topic. It's going to be a shallow dive because it can't be a deep dive. But a couple of people have asked me already tonight about memorizing the digits of pi. That's the next step. After you've calculated them and you've got a pile of 1,000 or however 10,000, there are people who, for fun, again, not for any deep reason, but for fun, try to memorize the first 1,000 or the first 10,000. The record is around 50,000, I think, which is pretty ridiculous, considering that they're totally random. But I'm going to show you how you too could easily memorize on the order of 1,000. This is the method I use to get from 250. I memorized the first 250 the hard way, which is just as numbers. And then I realized, like everyone does, this is not sustainable. You need to shift gears into some other technique. And again, this is like the Pilish technique. You can take this forever. Of course, it gets harder the longer it is. But so there's two key things here. We're going to associate words with digits. But the problem with Pilish is not a good memorizing tool because its efficiency is crummy. You get one digit per word, except for the 11s and 12s and stuff. You get one digit per word. What we want to get is 2 or 3 or 4 or 5 digits out of every word. And that is very possible. Step one you do is to associate letters with digits. And this goes back to this guy in 1842. This is all universally called the major system because it's by this major. And so I'll show you the exact mapping in a second. But this is the idea for that. And then the second one, I should probably get off of this slide because it's going to be just confusing at this point. So I'm trying to make it quick. So I'll show you the exact mapping here. The trick is you take 16 out of the 26 letters of the alphabet and assign them to represent a digit. And that can be a many-to-one mapping. So both S and Z represent 0, both T and D represent 1. And this is very clever because all the ones that have pairs sound alike. T sounds like D, and B sounds like P, and so forth. So those are easy to associate in your head. And there's a meta mnemonic over here for remembering how these map to the digits. And then the other 10 letters of the alphabet you just leave free. So you can sprinkle the free letters in with the forced letters to make words. And now there's a second thing you pile on top of that, which I was talking about with someone at dinner. You make these words, you can string them into phrases or sentences. And then the next thing you do is the state-of-the-art memory technique of today, which is usually called either a memory palace or the Roman room. And that's because this goes back to Roman times. This technique was very popular in ancient Rome for memorizing stuff. The thing they used it for mostly was they're giving a speech, they would memorize the key points of the speech. So not all 2,000 words they're going to say over the course of 25 minutes, but just the major points of the speech that they wanted to, major topics they wanted to touch on. Okay, so what is a memory palace? A memory palace is you take these sentences, these things you've made out of words using the major system, and you place them in your mind in locations, specific locations. Most common thing for a person nowadays to use would be like your house. You want it to be a place that's super, super familiar to you. And you put these in places, and then and you add on top of that another layer of, you make a path between the places. So you say, I'm going to walk in the front door of my house, and then first I'm going to go over to the dining room, and there's 1, 2, 3, 4 things in there that I want to take note of. And then I'm going to walk over here to the living room, and there's some things over there. So I have a path, and that's easy to remember because it goes through my house. And I'm going to show you the first room of my memory palace. And you'll see that the 4 things in there are also kind of connected in a way that you can see what that sequence is. So you don't have to think very much about that. And now you've got all of those major system encoded things in a sequence in your head, and you just have to translate those using the things shown on this slide. So here's the very beginning of my digits 251 through 768 that I made with this method. The really key thing, which I also mentioned over dinner to the person that was talking about this, is you make the things, the phrases and stuff you make out of the major system, you make those as wacky and crazy and weird as possible and personal. You can have people that you know in your life as part of one of your sentences. You can have anything that helps you. So you couldn't use my memory palace. It's 100% useless to you. You have to make your own, and you have to make your own major system words. So you put those together. Oh, good. The person. No, I won't go there yet. Okay. So the first one in my whole thing that I used to memorize 251 to 768 is a cup of tea with a flag on the toothpick. You've seen those flag on the toothpick things. And it happens to have Earl Grey tea in there. So that thing is the Earl Grey flag. And that gives you the digits 145648556 without any further thought. Over on the wall in the back, you'll see there's a picture of Mount Fuji with a gas station in front of it. That's a real place in Japan on the road to Mount Fuji. And that helps me just to know that that's a real place. And you can go and read articles about that specific gas station because it's famous for the one that as you're driving to Mount Fuji, you pull over and look, there's this great view of Mount Fuji. It sort of looks like it's on top of the convenience store. So all of that helps me to remember it. And then I made up the story in my head that I'm there driving on that road, and there's a person next to me, and I'm saying like, you know what this drive is like? We're in Japan now, of course. It's just like more gas and more Fuji. Everywhere you look, another gas station, another view of Mount Fuji. So that one is just Japan, more gas, more Fuji. But that gives you another 11 digits for very little mental work. Over here, you'll notice there's a pair of shorts. That happens to be in my fictional made-up thing. That happens to be of the Tommy Bahama brand. So there's a little playful little poem there about Tommy Bahama. His last name has 3 rhymes in it, Bahama. And I was able to include the concept of a serial rhymer into this sentence. He's a serial rhyming and grooving Tommy Bahama. So again, that's really easy to remember. Last one is the most easy to remember. I will never forget this one. This might be my favorite sentence in the whole section of digits from 251 to 768. Because over the years, for about the last 30, 40 years, I've been part of a small circle of friends who get together, not very often, but once in a while. Sometimes we're separated geographically. Doesn't happen that much. One of those friends has a particular talent, shall we say, for flatulence. Just thought I would bring that up because it's important. You need to know this. Sorry, this is only need to know stuff. It will be on the midterm, so they just do. I can't hide that fact. So now I carried it a little further in my mental thing. I said, we get together every once in a while. We're sitting around this dining room, and they start doing this. And one of the times when that happens, we start fighting back. So now it's going all over the place. And now there's also a very famous current, not like Brad Pitt level of fame, but a very famous and very super good actor, American actor. There's a trilogy of films called the Before trilogy, if you know what that means. He's in all of them, along with Julie Delpy. So he happens to be there at the same time that this is happening. And so the final salvo, shall we say, of this memorization of digits 251 to 300, that's what this covers, gets you up to 300, is that the gas exchanges that are happening are enrapturing Ethan Hawke. And with that, I think I am done. Or done for, or something.
Wow, thanks. Yay.